To answer the complex question posed in the video, we need to understand several fields that make up physics. For this, I have the support of National Geographic and their new collection, A Journey Through the Cosmos, which I am only relating to the video. But let's start with this pencil. Spin an egg like this, and something truly fascinating happens because the spinning speeding. My fingers is minuscule, but at the tip of the pencil, it's several times greater. Look, I understand that this might disappoint you a bit and not seem as amazing as it does to me, but let me explain. If we extend the pencil, the speed at the tip becomes increasingly higher until we reach a point where, as the equations of angular velocity tell us, not only do we reach, but we surpass the speed of light. From this point onward, nothing can surpass the speed of light. Right. Well, it depends on how you look at it. It's false, depending on the meaning you give to nothing and surpass. But don't panic yet. Existential crises come at the end of the video. While there are things that can travel faster than light, the example we just saw is not one of those cases. When we start to extend the cable, several problems arise. The first is the tension force. If you've ever used a yo-yo, you'll understand what I mean. A simple yo-yo spinning around you already exerts a notable force on the string, which has to be made of a resistant material to avoid breaking. Now, replace the yo-yo with an object moving thousands of times faster. We simply don't know of any material even remotely capable of withstanding the colossal centrifugal forces an object would experience approaching this speed. Then we have the necessary size because the cable itself also has its mass, which increases the force and structural requirements needed to support its own weight. This means the cable would need to be thickened to be sufficiently resistant to withstand the additional force. If we made it from carbon tubes, for example, to give you an idea, the base of the cable would need to be the size of the observable universe, although it would have collapsed into a black hole earlier, as we explained in one of our recent videos. Finally, there's a third little problem. Matter cannot travel at the speed of light because we would need infinite energy for that to happen. But these issues don't make it impossible directly per se. While these are impossible scenarios, they are not forbidden by the laws that govern the universe. The laws state that nothing can surpass light speed if it requires impossible materials or infinite energy. Everything we've just seen is not a solution to this problem. They are scientific excuses. The only solution will be found if we focus on the statement, because when we say nothing travels faster than c, nothing escapes us, not even the carriers of the fundamental forces of the universe and the bosons. The speed at which the cosmos communicates forces, among which is the electromagnetic one. If the tip of your cable were to reach the speed of light, the bosons in it could not transmit the information of the force that would keep it together, and it would break. In fact, not only that, but it would disintegrate instantly and cease to exist because the bosons responsible for carrying the strong nuclear force that allows atoms to exist would also stop doing their job. Here, we would indeed be directly violating a law imposed by the cosmos. The concept of a cable going faster than the speed of light thanks to centrifugal forces cannot exist in this universe, and that's it. But what can exist in this universe are lasers. Many observatories use powerful lasers to measure the distance the moon is moving away from our planet. Lasers that bounce off the mirrors installed by the astronauts of the Apollo missions allow us to calculate the exact time it takes for the laser, and therefore the distance. And this is thanks to the c we use to represent in equations the speed of light, c as a constant. If it weren't, such calculations would be impossible. But what happens if I take one of these super powerful lasers and point it at a new mirror, quickly moving the pointer across the surface of the moon? In a matter of milliseconds, it would have covered its entire surface. The pointer would have moved several times the speed of light. Did I see a point move faster than c? No, because we are witnessing an illusion that we actually experience all the time. Humans do not see individual photons, but the sum of them, a stream of photons hitting the moon's surface that continues traveling at c without anything really surpassing it, more than an illusion caused by its forced trajectory from Earth. They are just photons hitting the surface at the exact moment to make it seem like there is something moving, similar to domino paths where it seems like something is moving, though the pieces stay in their place. Anyway, it's not exactly the same because photons don't touch each other or need to be pushed to shine, but it's a good analogy. It's complicated. If we want to fix this, we'll have to get a bit transcendental. What does nothing mean when we say nothing can surpass C? Nothing is what we might call useful information, an extremely abstract concept, also the best way to describe it. Useful information can be your mother, our radio message, or the bosons we mentioned before, and the thing is, there is something in the cosmos that transmits non-useful information faster than the speed of light, quantum entanglement. Very succinctly, two photons can be separated by an observable universe between them, but if they are entangled, something we humans know how to do, which is why we have been able to verify that it works. And you calculate one of the variables of one of them, instantly, the other photon will know what its partner's variable was. But this is non-useful information. No matter how much you think about it, you will never be able to develop a useful system for transmitting information, neither Morse nor binary nor anything, because you can never control which value the variable collapses to in the photons. Nor do you know if the other photon has collapsed or not even when you make yours collapse. But this doesn't negate that they are communicating with each other instantly. And this is amazing because when you entangled them, you verified they were identical, but when you forced them to have properties, they never match. It's fascinating, but still non-useful information, so it remains useless. So let's go back to the statement and play with another word. What does surpass mean? Because let me tell you that with respect to a random planet in a very distant galaxy, right now you are moving several times faster than the speed of light. This is because we live in a universe with an ever faster expansion, and moreover, the peculiar way this expansion occurs makes it so that the more distance there is between two bodies, the more space there is between them, making the volume of that space gain more each passing second as it expands because everything is proportional, causing the farthest parts of the universe to be moving away from us at speeds greater than c. And here's the trick. You are not traveling through space faster than c. Rather, you are traveling with space at speeds greater than c, a very revolutionary concept that has inspired designs for spacecraft intended for interstellar travel. The so-called warp drive ships, which, by using negative energy, could create negative spacetime deformation, creating a wave to surf on, traveling thus with space much faster than light without really moving. These are very complex topics that we have only lightly touched upon today. For this reason, if you want to understand better about bosons, quantum entanglement, warp travel, or the model of cosmic expansion, I thought it would be a good idea to tell you about National Geographic's new collection in this video. It's called A Journey Through the Cosmos, and it covers in several books fascinating topics such as quantum spacetime, what existed before the Big Bang, or the Higgs boson. Honestly, after looking through the books and knowing some of the people who wrote them, I can say it's a highly recommendable collection. It's a high-quality, informative project supervised by a scientific committee aimed at a non-specialized audience through clear text, a wide range of images, infographics, and detailed drawings.